Hello everyone, I'm Alexey Pityuk. In our ongoing exploration of multi-material 3D printing, we are going to focus on improving our slicing and fabrication method to reduce the number of tool changes based on graph traversal optimization of individual material regions. As demonstrated in our previous example, the developed layer batching method provides a substantial reduction in material consumption and time required for multicolor 3D printing due to a significant decrease in wipe tower fabrication. The updated slicing and fabrication technique presented here is a tool change reduction strategy for multicolor or multi-material 3D printing designed for single-nozzle systems. It minimizes the number of tool changes by considering the existing layer height, maximum allowed layer batch size, and intersections with lower layer regions. The developed method utilizes the internal tools of the well-known Slick3R library and is compatible with modern Slick3R-based slicing software, for example, Prusa Slicer. Those familiar with multicolor 3D printing know that a significant portion of fabrication time is consumed by forming the wipe tower. This is due to the frequent material changes within almost every single layer, and the physical limitations of using a single extrusion tool, the nozzle. For each color transition within a layer, the material is switched, requiring the 3D printer to purge the new material from the same nozzle, and each purging segment takes time and contributes to the wipe tower formation. The layer is partially fabricated, and then, if a new material is required, the purging procedure repeats again. The iterative process continues until the entire part is complete. If we look closely at a layer slice of a multi-material model, in Prusa Slicer, for instance, we can notice that each color region is an independent G-code segment, or patch. This brings us to a fundamental question: can we reduce these tool changes by moving away from the traditional layer-wise concept towards independent interlayer fabrication of color regions? In other words, can we consider the model not as a set of layers, but as a set of individual color regions, and try to fabricate a part by traversing all these regions with minimal color changes, similar to minimizing distance when planning a route in the famous traveling salesman algorithm? Well, the short answer is yes. We can represent the model as a dependency graph of color/material regions and traverse it in a way we like. This video shows how to do that. Let's first look at the slicing process itself. Initially, the STL model is divided into a series of layers. Each layer is then subdivided into its constituent color or material regions, where for every region a G-code patch is generated. Subsequently, an internal tool ordering procedure determines the sequence in which these regional patches are fabricated. In this context, the concept of the layer is important for preserving information about the vertical size of the structure, particularly for the possible placement of support layers. The support layers, however, can be made in any color, so we do not have to worry about keeping the same material here. Another internal tool ordering algorithm analyzes the number of material transitions required during fabrication, and the G-code for the wipe tower is concurrently generated. Therefore, by optimizing the G-code fabrication and tool ordering steps by reordering individual color regions, we can substantially decrease the number of tool changes and, consequently, the size of the wipe tower. As for the support layers, we can simply insert them between the color regions while maintaining the vertical height position. The slicing method is compatible with many modern slicers built on the Slick3R library. In this example, the method for reducing tool changes was developed based on the Prusa Slicer. Let's now look at our sample model, segmented into layers and color regions. This step will show us how the original 3D model can be represented as a dependency graph for future traversal. Upon initial slicing, we take into account the height of the layers, which is important because the nozzle size determines the thickness of these color areas. So our model consists of 13 layers and 5 colors. This information is needed to transform the model into a set of layers, each of which is then segmented into separate color regions. This leads us to a node notation, where each color region will be represented as an individual node in the future graph. These nodes can be denoted as LX or Y, where L signifies the layer number, X, and R represents the region number, Y. For example, layer 7, region 0, purple color, would be denoted as L7R0, and region 1, white color, would be denoted as node L7R1. In designing the traditional fabrication process, consider the bottom layer number 0. First, we can print region 0, then region 1, and then region 3. With the single nozzle system, each transition between regions requires a material change, also called a filament change, color change, or material transition. Similarly, within the first layer, moving from region 3 to regions 1, 2, and 0 respectively, will also result in a tool change. This continues sequentially until the final piece of layer 12 is completed. For example, using the standard Prusa slicer configuration, this model would typically require 28 tool changes. The question remains, can we reduce the number of tool changes? Well, we can do this by going beyond the traditional concept of printing one layer at a time. As illustrated in our previous video, using the layer batching technique, it's possible to print multiple regions of the same color across several layers, then return to print another color for a few layers, and so on. This approach significantly reduces the overall number of material transitions to complete the part. One effective strategy for such reduction is to represent the model as a graph, and then traverse that graph in a way that minimizes tool changes. In Prusa Slicer, for every color region, we can extract information such as its X and Y location, Z height, its area and perimeter. And most importantly, we can also calculate the intersection with other regions below. This will give us information about whether the color region can be 3D printed in a given layer, or whether we should finish printing the color regions on a layer below, before moving on to the upper layer. For instance, in the presented model table, which can be generated directly in Prusa Slicer, region and tool are synonymous. We track the layer and region numbers, where the region number corresponds to the tool, or filament color and material. Columns marked with asterisks indicate intersections with regions located directly one layer below. For layer 0, we see three color regions, purple, white, and yellow, while pink and green regions are missing, indicated by the 0 area, so the exist column is set to 0. Since this is our very first layer, there are no previous material intersections with the layers below, so all intersection values, asterisk columns, are 0. Moving to layer 1, the green region remains absent. However, the region L1R0 intersects with the region L0R0 below, and similarly, the region L1R1 intersects with its predecessor, the region L0R1. The pink region L1R2 appears for the first time in this layer and does not intersect anything. The yellow region L1R3 intersects with the yellow region L0R3 below. In this way, nodes L1R0, L1R1, and L1R3 in the graph are connected to nodes L0R0, L0R1, and L0R3 respectively. This means, for example, that region L0R0 must be fabricated first, before fabrication of region L1R0 can proceed. Since the pink region L1R2 is new and there is no any connection with regions below, additional connections are made with all other nodes around it to ensure the structural integrity of subsequent layers. Thus, we assume that in order to fabricate this pink region, all surrounding regions must be fabricated first, which implies a dependency on fabricating those regions. Looking at layer 11, there is only one green region left, L11R4, intersecting with the purple region L10R0 and the green region L10R4 on the layer below. To complete printing this green region on layer 11, we must first print both the purple L10R0 and green L10R4 regions on layer 10, which is immediately below it. Therefore, region L11R4 cannot be printed until regions L10R0 and L10R4 are completed. The animation shows the layer-by-layer generation of our dependency graph. This graph visually represents how each color region depends on all preceding regions below it. When a graph node, representing a color region, has connections below, it signifies that these underlying regions must be fabricated first to successfully print the given region. A node can only be fabricated once all of its connections or edges below it have been fabricated first. In traditional slicing and then 3D printing, we proceed layer by layer, changing tools multiple times within each layer. Optimization in this zigzag approach is mostly limited between successive layers. A new layer tends to start with the same material as the last region of the previous layer, thereby minimizing a single tool change. However, there are still a significant number of tool changes within layers. But can we, for instance, eliminate the zigzag layer-wise manufacturing concept and instead process individual nodes, color regions, independently? Can we fabricate multiple regions of the same color and then return to the lower layers and continue printing other regions, switching colors as needed? This is where the concept of layer batch printing comes into play. In this example, we have 3 layer batches. This means that we are fabricating regions of the same color in a maximum height of 3 layers, compared to the lowest layer among previously fabricated regions. Here, if we start with the purple material, we fabricate 3 purple regions L0R0, L1R0, and L2R0, one after another across 3 layers L0, L1, and L2. This is our first 3-layer batch. Then we return to the layer L0 and fabricate 3 white regions L0R1, L1R1, and L2R1 across 3 layers, the second batch. At each step, we analyze whether it's possible to fabricate the same color on the upper layer, or in other words, to maintain the same region across several layers. If the number of layers in the batch exceeds the batch number specified at the beginning, or it is physically impossible to fabricate the next region without completing the other regions below due to region intersection, we make a random jump to another color and continue the process again. In batch number 3 then, yellow regions from L0R3 to L3R3, we fabricate the same yellow material over 4 layers, since the maximum layer distance between L3R3 and the remaining unfinished region L1R2 remains within the maximum layer batch range of 3 layers. When we jump to the region L3R0 later, we only fabricate the purple material up to the region L4R0 because it's not possible to continue fabricating the region L5R0 due to the intersection with the unfinished region L4R1 connected to L5R0. This optimized approach reduces the total number of tool changes to 15. This means that the wipe tower only requires 15 additional slices, almost halving the regular wipe tower size. To visualize this, we can represent the manufacturing order or printing map by changing the colors of each fabricated batch. This allows us to see how we move through the nodes to complete the entire model. One of the key ideas of this graph traversal algorithm is the concept of random jumps. For example, if we start with the purple region L0R0 and fabricate purple material up to region L2R0, we can then switch to regions L0R1 or L0R3, as both options are possible. We analyze the potential regions for jumping and then randomly choose one of them. The same procedure happens after each batch. This gives us multiple options for generating a fabricating path for the same model. Here, the animation further illustrates the differences in the fabrication process between regular and batched fabrication described earlier. And as mentioned above, this isn't the only possible fabrication sequence. We can generate numerous alternative print paths due to random jumps after each processed batch. The 2 parameters we can vary are the batch size, be the number of layers we can cover in one batch, and the starting color region. Once a batch is completed, 3 layers of region 0 in the first image on the left, for example, we can randomly switch to another material and jump to any other available region below. After finishing with region 0, we can move on to region 1 or region 3, but not to region 2, since it doesn't yet exist, or it can be printed until its dependent nodes are complete. And here is another animation for these alternative paths. Well, we can generate more unique fabrication paths, and more. In fact, by performing 9,000 iterations, 1,000 iterations for each combination of batch and starting node, we can clearly see the distribution of tool changes for different initial parameters. While the standard slicer approach would result in 28 tool changes, our iterations show varying distributions, all of which remain less than 28. Our objective here is to choose the optimal way to fabricate the existing model with the fewest possible tool changes. For example, for a batch size equal to 3 layers, b equals 3, we can choose the optimal fabrication path with the fewest tool changes across multiple starting nodes. Similarly, we can define the minimum number of tool changes for batches of different sizes, b equals to 3, 4, and 5, starting from the same material region, for example L0R0. This allows us to visualize the best paths for a certain batch size. or starting node, and compare the best and the worst paths across all iterations. It is important to acknowledge, though, the inevitable damage that may occur to the fabricated underlying layers. When the hot nozzle returns to print new material that comes into contact with the already printed batch, some aesthetic defects might take place due to the size of the nozzle and the height of the batch. However, in most cases, these damaged areas are internal and therefore invisible. For example, if we increase the batch number to 6, meaning 6 layers of the same color are printed consecutively before switching to another batch, a wavy pattern may appear on the yellow part. Yet this pattern is not visible on the purple section because it's located deeper in the model. Here are a few more cases to support this statement. Thus, the transition from traditional layer-by-layer 3D printing to sequential fabrication of individual color regions across multiple layers allows for a reduction in the number of material changes while maintaining acceptable manufacturing standards. Well, thank you for watching and choose the right fabrication path.